Hello and welcome to Wacko Breaking It Down with the warm up for logarithms. This is towards the beginning of the unit and just some basics that we need to know. You should have already kind of explored what a graph of a log looks like and understand that a logarithm is the inverse of an exponential. So when we work with all these things, that's what you have to keep in mind. I think the main thing, you know how we worked with the inverses before? Let me give you some different examples of things we've worked with. Like if I had x to the squared, you would say, well, the inverse of that would be square root. Actually, let me write it as a separate function. So we'd have these two different functions, but these are inverses of each other because if I take one, I take the whole thing of one and put it in for x in the second one, like so. If you simplify it, it should come out to equal just x. And that's kind of how you check to see if something is an inverse or not, or if two functions are inverses of each other, right? And I could do it that way. And I could also take this whole guy and stick it in going this way and end up with something that looked like this, right? And that also, right, we all know a square and a square root cancel each other, so I just end up with x. So either way that you substitute one function into the other, you should end up with just x after you simplify it. That's how you know they're inverses of each other. So when we look at a log, and it doesn't matter what base, let me just start off with base 10. By the way, right, just as a reminder, if there's nothing written down below here, then we automatically assume it's base 10. So if I take the inverse, or sorry, take the exponential with the base 10 and a log with base 10, and I put one inside of each other. So one way to do it would be to put the 10x inside of this one. So I'm going to take all of this and stick it into this x. Okay, whoops, went too far. So if I do that, it'll look something like this. I'll have log base 10, and I'm just not going to write the 10 because it's assumed we already know that. And put that inside of it. I mean, I can write it down here real quick, the base 10, just so you can see it. But if this base and this base match, they're inverses of each other. Remember, we always said you roll the logs. So you take this number, this base down here, to this power, and it will equal what's on the inside of the log. We call that rolling the log. So 10 to what power will equal 10 to the x? Well, obviously it has to be x, because 10 to the x power equals 10 to the x. I mean, it has to be. It can't be anything else. So that is kind of one way to show that these are inverses of each other, right? By composite functions. We've done composite functions before. It doesn't matter. Let me say this is a base 5, let's say. And yeah, base 5. And if I had 5 to the x, it would work the same way, right? I could take this 5x, sorry, and stick it inside of here, log base 5 of 5 to the x. And I ask myself, what power do I need? 5 to what power equals 5 to the x? Well, again, it's just going to be x. Those are inverses of each other because they have that same base, a log base 5 with a base 5 on my exponential. So that's kind of how inverses work. And by the way, you can do this the other way, just like when we worked with other inverses. I can take all of this and stick it into that x. Ooh, 5 raised to the log base 5. This is harder to understand logically, but it's just to let you know it does work. So if I put that up there, since I know that 5 to the x and log base 5 of x are inverse functions, I know that when I put this in here, this is just going to equal x. And again, it's intuitively, it's hard to understand a little bit, but it works because we know they're inverses. So whenever you see those composites like that, you can always just simplify it down to x, whatever inside. Right? So keep that in mind as we go through there. So I look at this, I'm like, okay, what number, pi to what number? And you see how since these are the same, it doesn't really even matter what they are. It could be a pi or a 10 or well, not infinity maybe, but it could be 72, right? Or anything. When I take that to what power, when I ask myself what power gives me the inside piece, it's the only option is 4, right? Because I have to have 4 as a power, so this has to be 4. So I look at that and I say, oh, the answer is 4. I'm done. As long as these bases are the same. This one, same thing, but I have to do a little work to kind of finagle this part of it first. And by the way, this really is parentheses like this. Technically speaking, it's the log of this whole thing. A lot of times we leave it off, even though it really is there. I have to finagle the 1 over 27 on this part B. So 27 is the same as 3 to the negative third power. That's what we have to realize. So this is now gone, and I have 3 to the negative 3 power. Stop it and work with that if you need to figure that out. But 27 is 3 to the third, and then I move it. If I flip it back over, I'm going to get a negative power, right? Okay, so if it's log base 3 of base 3, and that's kind of the reason I had to change things around, is I need those bases to be the same if I'm going to use that inverse idea. Now, once I've got the bases the same, then the rest is easy. You just look up here and say, oh, that's negative 3, and that's your answer. You're just looking for the power. Log base 10 equals 0, and you're asking 10 to what power equals 0? That's actually impossible. If you remember from the graph of a log, let me do it this way. A log kind of goes like this, and it approaches the y-axis, but it never crosses it. So it's never ever going to equal 0. It's just going to get closer and closer and closer to it, but it'll never equal it. So this is undefined. There's no power that will make that equal to 0. 10 to some power. So undefined. Log pi of 1. The only thing the only power of something that can make it equal to 1 is 0. But the good news is it works no matter what the base is. Whoever wrote this is using pi to kind of show you that it doesn't matter what that base is. This could be 12 or 632. It doesn't matter. If it's to the 0 power, it's going to equal 1. Same thing here, right? It doesn't matter what these bases are on part A. As long as they're the same, it's going to be 4 every time. Okay, so that's a little insight, rolling the log, and kind of thinking about logs and exponentials as inverses. Right, so now we have log base 2. I always look at this base right away to make sure I know what I'm dealing with. Remember, the inverse of that would be 2 to the x, not 10 to the x or anything else. It has to be the same base. Those are inverses, but I don't know if that's important for this problem. It says plot at least 3 points and the vertical asymptote. Well, we haven't done any shifting on this yet. I think we're going to save that for later lessons. So for right now, it's just plotting points, just knowing how they work. So if I say log base 2, but I put in a 1 into that equation, I'm asking myself what power, or in other words, what y value, 2 to what power equals the 1? Well, that has to be 0, so that's why you see this number over here, right? This 0.10 over there. If I put in 2 into this, right? I should leave that off for the moment because this will stay the same. Okay, if I put 2 into my equation, now remember this is where the x is, and then the y value is the power. So these y values, this is 0 and this 2 and all these y values, those are the actual power on the base. So 2 to what power is the y value equals the x value. So 2 to the first power is equal to 2. So that's really not shown on here, but it is a point, like this point right here. I can see it, right? I could have one, whoops, sorry. It's always backwards, right? The x value is 2, and then the y value is the 1, right? 2 to the first power is 2. 3 wouldn't come up very nicely because it's not a power of 2. All right, but if I put in 4, right, I'm kind of looking for powers of 2. 2 to the second power is 4, so 4, 2. 2 to the 8th, or 2 to the third power is equal to 8. So I'm kind of going 2 to the first, 2 to the second, 2 to the third, right? And equals 8. So that gives me 8, 3. It's kind of like when we're rolling the log to think of our numbers, we're undoing that inverse. But remember, when you plot them, it's really the inverse of an exponential. So if you remember right, my exponential to this, like if I were to take y equals 2x, that's the inverse to this, I would be going, 2 to the 0 power would be 1, 2 to the first power would be 2, 2 to the second power would be 4, 2 to the third power would be 8, right? And you'd see that this 2 to the x, this exponential, with an asymptote on the x-axis, right, would be the inverse of this logarithm. How do I know? Well, I know it, but also if I look at the y equals x line right through the middle there, you can see how those are reflections of each other. One's, if you flip one over, like this point, for example, if I just go straight perpendicular across that y equals x line, instead of 4, 2, now I have 2, 4, right? You notice, remember when we talked about the points on an inverse would switch? Well, that's exactly what's happening, right? So the 4 and 2 and 2, 4, they switch, and all the other points too. 1, 0 becomes 0, 1, and 8, 3 becomes 3, 8. So those are directly related because they're inverse functions of each other. You just need to get used to plotting points though, right? 2 to what power equals the inside piece. But remember, it's kind of backwards. The x is what it's equal, and the y value is the power. All right. We're looking for powers of 10. So 100 is 10 squared, so we just rewrite that. 1,000 is 10 to the fourth. 1,000,000 is 10 to the sixth. This is just getting used to decimals. 0.01 is 10 to the negative 2, right? We're moving the decimal 2 places to the left. This is 0.001, so I'd have to move the decimal 3 places to the left to get this negative 3. We want you to be really careful though, because this negative has nothing to do with the power. It's just a negative number, so that stays there as a negative number. Here I'm moving 1, 2, 3, 4, right? So the power, remember, is directly related to a logarithm. Okay, estimate first and then use your calculator check. So we did this kind of estimation, or we did this kind of thing up here. So we could estimate from a power of 10 some of these numbers. Like 345, for example, is somewhere between 100 and 1,000. They didn't put 10,000. If there was 1,000 here, sorry, right, that's 10 to the third, right? So 345 is somewhere between 100 and 1,000. So my power is going to be somewhere between 2 and 3 to give me that number. 345 is closer to 100 than it is to 1,000. So it's a little less than 2.5, like 2.4, 2.3, maybe even less. And if you look at the real answer, it comes out to 2.2. 2.2. All right. Same thing. Let's look at this one, 3.45. Well, that's between, a 1 and a 10. 10 to the 0 would be equal to 1. 10 to the first would be equal to 10. So what power is going to give me 3.45? Well, again, it's kind of in the middle, but it's a little closer to the 1. So it's somewhere between 0 and 1, so like a half, and it is like it's a half. All right, I know it doesn't always come out exactly. We're kind of estimating right now, but let's look at a calculator. How would we figure that out on a calculator? Well, you can guess and check a little bit, but you can also solve. So I'm going to do this. I'm going to say 10 to what power, right, equals, and let's do the 345, equals 345. So this is really important because this is how you solve equations. So this is the first time I'm really introducing how to solve equations when you have an unknown power, right? And when we did the previous unit, we always said you had to use your calculator and graph it and look at the graph and look for the intersections. Well, from now on, you don't have to do that. So here's what we do. If this is a base 10, and no matter what this base is, I'm going to use the exact same base. Remember at the beginning of this, I talked about how we have inverses if they're the same base. I want to make this an inverse. So what I'm going to do is choose a log that has the exact same base. So I'm going to use log base 10. And then of that, so when I say of that, I'm really mean of it, like the whole, I'm doing the log of the whole side of that equation. And remember, if I want to keep my equation balanced, I have to do log base 10 of the right-hand side. So I'll do log base 10 of this whole side, which is 345. Sorry, this thing doesn't write very nicely, but hopefully you can follow. All right, now why does this help? It looks more complicated, Mr. Waka. Well, it won't in about 2 seconds. Remember up above when we were beginning, we said the log base 10 of a base 10 are inverses of each other. So this whole thing, I know, just equals x. 10 to what power equals 10 to the x? Well, x. So that just equals x. And then this on the right-hand side is just something I can throw in my calculator and get a number. So let's do that. The log base 10 of 345. So I'm going to grab my calculator. Just for fun, I'll put in a new doc to get a nice fresh doc. And then you can see it. You can see I have a log button on my calculator over here. See where it says log in blue there? And when you hit that, it'll let you put in whatever base you want. I want log base 10 in this case, but you can put in anything you want. We'll do log of 345. I'm going to put in a decimal into here so that I get a decimal answer. If I don't, it just repeats it and it doesn't help me. So let's put a decimal inside this so that it'll give me a decimal out. So that's 2.54 basically. 2.54. If I go back here, then this 2.2 is actually wrong. It should be 2.54. So that should be like 2.5. Whoops, missed it. Come on. There we go. So the real answer I can see is 2.54. I'll estimate it at 2.5. Like before we were doing an estimate, right? So we were allowed to estimate. That's why they were different. Let's check out the 3.45. I'm doing the exact same thing, but instead of 345, I'm just going to put a decimal right here. But we're still going to do log base 10 on both sides because we're talking about base 10. So all I have to do is copy this down, change my decimal to 3.45, and we get 0.54. So that's almost the same, right? I could do 0.54 like that and like that, yeah. We're supposed to be estimating, that's why we didn't write like a nice perfect decimal to it or anything, but okay, that's how you solve an equation. It's so powerful. From this point on, you can solve equations where you don't know the unknowns by doing that. Let me just do one more just so you know. So let's say I have an equation like, let me go to the calculator page here so we can do it right underneath there. All right, so let's say down here I have some equation, 1,127 bacteria remaining after I started with 212 to begin with. And I had an increasing rate of 3% per day. And I want to know how many days it takes to get to 1127. So we do logarithm both sides. What? This isn't base 10 anymore, Waka. That's okay. Sorry. Divide by the 212 first. So that's kind of the big thing. My base, I'm looking at all this going, what's my base? What's my base? The base is what you have the power to. So this is 1.03. I have to get everything away from that first. So I'm going to divide by 212. Get rid of that and just get a number. So you can see up here, I'm just going to take 1127, divide by 212. I get 5.31. It's okay if I work with decimals. 5.316 equals this, right? 1.03. You'll notice I'm leaving room on purpose because I I know I'm going to do the logarithm of both sides. Okay, so I just move that over. Now, to solve, I need to do the logarithm of both sides. Am I doing base 10? No, I am not. I'm not doing base 10. I am doing base 1.03. What? Yes, 1.03 base. Am I allowed to do that? Yes, you are. So there you go, 1.03 base. I'm going to do that over here, 1.03 base. Very strange, Waka. Yeah, but that's okay. We can have a base of anything we want. If I can do it as a rate, I can do it as a base. Okay? So the one on the right is the inverses, right? These are inverse functions of each other. So this whole thing just equals x. And then all I have to do is plug the left-hand side into my calculator here. So let me do log. Again, I need base 1.03. And then raise to the 5 point. Instead of writing it out, I'm just going to copy this down. So what I do is arrow up and then hit enter. And that way it'll make it super accurate, right? It won't be rounded. So 56.5 days later, my bacteria would have grown from 212 to 1,127, assuming a daily growth rate of 3%. That's how you solve using logarithms. You're welcome. Okay, that's the end of the video. This is just supposed to be the warm-up, right? So that's a good little lesson just for the warm-up. All right, good luck working problems. Now you got a new powerful tool.